So talk about like polynomial identity testing. That's what I was saying, but I don't think it is. So this is like what almost all of ZK, mostly like univariate ZK, is based on, right? Because multilinear is like some check and zero check and all that stuff. So what's starting with a problem? The problem is polynomial identity testing. I want to figure out whether a polynomial, whether two polynomials are the same. Okay? So you have two univariate polynomials, and you want to know whether the two of them are exactly the same. So an example is like x plus 1, x plus 2, right? This polynomial, if you expand it out, that was like x squared plus 2x plus x plus 2, right? As x squared plus 3x plus 2. So technically, these two polynomials are the same, right? But it might not necessarily be obvious all the time. So one way you could do this is, so how would you determine whether these two polynomials are the same? Let's say they just give you this and this. How can you tell if they are the same? Yeah. They gave you the left side, they gave you the right side. You expand the left side, right? You evaluate at random points.
Many random points.
So
evaluate at points that will turn them 0 and see if they go 0.
Evaluate at points that will turn them 0 and see if they're 0. Okay, so there are like 3 ways now that have been. You factorize the one on the other side. So now imagine if they give you something that looks like this. X plus 5 raised to the power of 1, right? Is equal to x squared plus 9x. Wait. Let me try and make it possible-ish. Now it's not so obvious that it should not be so obvious, hopefully, that it's not possible. So how would you test, or how would you know if these two polynomials are? You could also factorize, you could expand, right? Yeah, that's minus in the middle. So that it's like, it shouldn't look, wait, this doesn't even work. Let me put 100 here too.
Difference of two squares. This is the same power.
Sorry, let me put. My point is that I wanted to not, like, by looking at this, you cannot just know whether they are the same, right? It's ambiguous a bit, yeah.
So you have to analyze that, like evaluate at multiple points.
You also evaluate at multiple points. Maybe?
Oh, like what I said, x squared plus 9 is equal to 0. What point to make it 0? Evaluate at
Maybe.
It means you have to look at
I'll go right side.
Exactly. So let's now go to a different problem that will help us solve this problem once we solve that problem. So let's say we had a polynomial p of x. How do we know if this polynomial is the zero polynomial? Do you know what the zero polynomial is? The zero polynomial is a polynomial that, regardless of where you evaluate it at, it's always 0. So p of x equals 0 is the zero polynomial. Because there's no x here, right? So even if I do p of 1, it's still 0. If I do p of 2, it's still 0. So how can you test easily that a polynomial is the zero polynomial? Huh?
Evaluate at
Any point.
different points and
So you evaluate at any point. You said different points. So if I evaluate at any point, it can give you 0, right?
Yeah.
But does that guarantee that it is 0?
Like, what's the point?
How many times?
Like,
How many times do you need to do it before you are like sure that okay, yeah, this is 0? Depends on the degree. Depends on the degree. So there's a link somehow between degree and zeros. That's one of the things I want you guys to internalize, right? So let's talk about degree a bit. So degree tells you how many roots a polynomial has. I think what does it do? Is it the maximum number of, so that's like a straight line, right? That's degree 1. It has just 1 root. So a quadratic, that's 2 roots, right?
degree is equals to
Yes, exactly. So this is it. The degree is equal to the number of roots of a polynomial. Then what's the root? The root of a polynomial, what does it tell you about the polynomial?
If
Yeah.
you evaluate polynomial at the root, you get 0.
Exactly. So if you evaluate a polynomial at the roots, you are going to get 0. Okay? So P evaluated at roots, let's say this has like 5 roots. If you evaluate at the first root, you are going to get 0. If you evaluate at the second root, you're also going to get 0. Evaluate at all the roots, you are going to get 0. Yeah. Okay. So why is this? Give me a second. Okay. So that's this is a line, right? P of x is equal to 2x plus 1, for example. What's the root of this polynomial? Does that make sense? So P of minus 1 over 2 or minus 0.5 is equal to 2 times minus 1 over 2, right? Plus 1, which is equal to minus 1 plus 1, which is equal to 0. This is a degree 1 polynomial, meaning that it has only one root. That means that there's only one place that you can evaluate this polynomial that you are going to get 0. Because that's the thing that you evaluate P of x at that will give you 0. So the way you get the root is that you solve for 0. Right? So 2x is equal to, so you are trying to find the x's that will make this. Then it's now be like 2x is equal to minus 1. Then x is equal to minus 1. Does it make sense? So this is what we're doing in secondary school, like quadratic polynomials, right? So let's say you had like x squared plus 2x plus 3, for example, right? To get the roots, you do equals to 0, right? Then you factorize out, and you're supposed to get like 2 roots usually, right? So that's why this is a degree 2 polynomial, meaning that it has 2 roots. So there are only 2 values of x that you can evaluate this at, that it will give you 0. That should start to give you a clue as to how you can check that a polynomial is a 0 polynomial. Who can relate those two? So now we know the degree is the same thing as number of roots. And we know the number of roots now tells us like the points that we can evaluate a polynomial to get 0. And that's the maximum. Maximum. Or exact. It's not even the maximum, it's exact. It's just that the answer can be in like complex and it can be in reals, but yes, so every number is a root of a 0 polynomial. Okay? But then now we're with a polynomial that we don't know if it's actually a 0 polynomial. Like we don't know if it's a 0 polynomial or not a 0 polynomial. So how can we test that this is a 0 polynomial?
Without evaluating at several points.
You could evaluate at several points. If you have an algorithm that can do it by evaluating at several points.
Maybe you can find one number that is not, that when you evaluate the polynomial at, it doesn't give 0.
Yes, so how would you search? Like the problem that how do we know when to stop, right? So maybe we can guess a point, right? That's like 5, and you evaluate it. I might give you 0, but that doesn't prove that it's a 0 polynomial, right? Because that could have been one of the roots.
You check as much as you
Okay, plus 1.
Oh, okay.
You stop at n plus 1. The degree plus 1.
Does it make sense?
do.
So the degree, so like every degree D polynomial has D roots. Okay? So if it's evaluated at D points, there's a chance that those D points are all the degrees. You were just lucky, you got the first root, second root, third root, fourth root, D roots. So when you will now know whether it is actually a P of 0 polynomial, a 0 polynomial or not, is when you now evaluate it at another point outside of D. Because if it's a 0 polynomial, then that will still be 0.
Yeah.
But if it's a, then that one would like be non-zero for sure, right? Because we have already seen all the D roots. Does that make sense?
So that means something as to get the number of people you need like the T plus 1 points.
There might be a relationship there. Yeah. There might be a relationship there. But I can't see it yet. But there might be a relationship there. Can I explore it a bit there, see if you find anything useful there? Yes. Yes. You can't have more than 2 points that when you evaluate it as you get 0. So the degree puts a bound on the number of roots of that polynomial, right? So that means that if you want to check if a polynomial is a 0 polynomial, all you need to do is just what? If you want to like be 100% sure, 100% is very important. This 100% is very important. If you want to be 100% sure, all you need to do is evaluate it at D plus 1 points, right? And see if you get a non-zero, right? It's not sufficient to evaluate at just D points, right? In most cases it will work, but it's not sufficient. Because those D points that I might pick might be the D roots by mistake, right? And then you will now say, oh, they were all zeros, and then you'll be happy. Whereas, if you had picked one more point, it would have been a non-zero. Does it make sense? Sure? Yeah.
So like, how would you like get this roots exactly? Because we are trying to evaluate that with input of numbers. That means we are sure that you evaluated all like all of the roots.
Okay.
So what if you didn't get all of the roots at the first place or the first degree?
No, the point is that it doesn't matter, right? Because of when you're trying to do that, you are looking for where it will not be 0. So you're not even trying to find the degree. You're not even trying to find the roots. Sorry. Like a 0 polynomial, regardless of the point you evaluate at, is always going to be 0. But then this other one is like you don't know whether it's a 0 polynomial or not. So you need to evaluate it at. You want to see, like if you evaluate at the first point and it is not 0, then you're done, right? Like you have already verified that this is not a 0 polynomial. So you are done already. So you are welcoming the cases. You are not like actively trying to find the degree. So why we're saying D plus 1 is because of we want to rule out chance, right? Yes. So because the first D you might pick, by chance it might be the first root. So it will be 0. Then you think that okay, this might be a 0 polynomial. Then the second one you pick, it might also be 0. You think this is a 0 polynomial. If you stop at D, by chance you might have picked all the D roots. So by picking one more, you can't like guarantee that this last one is not a root at all. So that's the one that would differentiate really whether, but any of the previous ones could have differentiated. Did you get? Does it make sense? Is there any question? It's the same thing.
Now, this is what I'm saying. Let's say you don't have
Okay.
He wants to be finding
Yeah, it's large.
very
Yes. But that's
that kind of show.
that's so that's the point. Like, we're going for 100% sureness now. So you do have to do like 100 plus 1, right? So that's the degree. That's the only way that you can be 100% sure. But then we'll now look at ways that you might not necessarily be 100% sure. Maybe like 99.99999% sure. And that's fine. You get. So ZK is a probabilistic system in the sense that we sacrifice some of that guarantee or that 100%ness in order for us to do things like faster and more succinctly. Okay, so now we know how to test if a polynomial is 0 or not 0, right? So how can we use this to test if two polynomials are the same?
Two polynomials will be the same if they are the same.
Okay. But how will you? So how will you not use that?
If they are the same probability.
Huh?
If they are both non-zero and that's the
These evaluations are the same.
There's one key idea. Like, can you relate it to this?
If you evaluate them at the same
I think all these are correct technically,
And like if you evaluate
but I'm
them
still looking for one idea.
if you evaluate them at those different points and at least it was one time, like it was one number of times, like you should give the same exact evaluations at those people of one point.
Yes, they're all correct. Like, you guys are actually all correct, but there's something I'm looking for.
Okay, if the equal if I'm just thinking about if you subtract them, subtraction gives
That's
you
what
zero.
I'm looking for. Yes. So, if you subtract them, if they're the same, it's going to be 0, right? Like a minus a is 0. But if they're not the same, then you get another polynomial. Now you have a polynomial that you don't know whether it's a 0 polynomial or it's whether it's a 0 polynomial or not, right? So all you can just do is just test with this thing that we have, right? So let's say you had a polynomial p of a, and you had another polynomial p of b, and you're trying to determine whether these two polynomials are the same. All you need to do is just subtract. So when you subtract, you're going to get a new polynomial, let's say p of c. Now, if this p of c is 0, then that means the two polynomials are the same. But if p of c is not 0, it means that the two polynomials must have been different. So all you need to do now is just figure out, like, which is what we have shown so far, right? Just evaluate it at d plus 1 point and see if they're all zeros. If they're all zeros, then you know that the two of them are the same,
So
right?
it's possible for us to subtract a from b and our results still point us to the fact that they are the same.
Yeah. Like, if they're the same, it will be 0, right?
I was thinking probably they are the same, we should cancel each other out.
Exactly, that's the point. It will be 0.
But if they not give us another polynomial that if we evaluate them and choose t plus 1 plus plus of 0, is that possible?
What do you mean?
That this schema,
Yeah.
we might evaluate them at all those 2 plus 1 points, and we have 0.
Yeah, when at d plus 1 point and you have 0, the answer that polynomial is 0.
And that's what I'm saying that I'm thinking that if this A and B are the same, we should cancel each other out by subtracting them,
Yeah.
not having another polynomial.
No, so it depends on the structure of the polynomial, right? Like, imagine this case where you had this and this, right? You might subtract them out without simplifying. Do you get? So the subtraction is going to be like x plus 5, 100 minus x minus 6 plus 5x, 101 minus x squared plus 9x is equal to, let's say, p of c, right? So this is your p of c. And this is the polynomial you want to test. So you don't need to simplify. All you now need to do is just evaluate it at d plus 1 point and see if all of them give you 0. Like, it's simpler to, like, if let's say x was 0 now, right? 0 plus 5 is 5, then 5 raised to the power of 100. It's easier to do than expanding x plus 5 raised to the power of 100. Right, that's just like 5 raised to the power of 100, and the computer can do that easily, right? Do you get? Rather than now doing like x plus 5 times x plus 5 100 times. So you don't need to simplify. You just do like the compound f of c equation, and then you just evaluate at d plus 1 point. Does that make sense? Wait, we're not done yet with the.
When you subtract and
Yes.
minus just
Yes. When you subtract two polynomials, the degree can never grow, right? Degree only grows when you multiply. So the degree can never grow. The degree can reduce, but to be on the safe side, just assume that the degree is the same. Yeah. You just go with the highest here. So you evaluate at 101 plus 1 point. Yes, 102 points. Okay? We'll do an example. Don't worry. Oh, what I'll now say is that, okay, so this is how we can now determine if two polynomials are different. So this should now like link us to the fact, to the Schwartz-Zippel lemma basically. Which basically says that if you have 2 degree d polynomials, those polynomials will agree at a maximum of d points and not more. Is it d points or d plus 1 points?
D.
It should be d, right? I think it should be d. Why d plus 1? Why would it be d plus 1?
So evaluate for subtraction to be that we are checking to d plus 1. So if both of them do not get d plus 1, then that evaluation doesn't count. That d plus 1 extra evaluation.
I think it's d.
Why do you think it's d?
Because of the degree, let's say like degree d and degree d, right? When you subtract, you are either going to get all zeros, or you're only going to get zeros at d points. For you to get zeros at d points, it means that there must have been an alignment between the two of them at those d points. You get not d plus 1 points. We need to do an example. It's getting very abstract now. Yeah?
Please, can you go back to the former?
Which one? The 2x plus 1?
No, this power.
Okay.
So my question is, you said we should give 101.
Yeah.
But if we evaluate
102 times.
Okay, 102 times.
Yeah.
But if we evaluate at 2 points and we get a 0
Yeah, right at
2 points, we get a 0.
so you said you are trying to evaluate at 101, 102 points.
Yes.
You have evaluated at the first one, and you have evaluated at the second one,
Then the third one.
and the third one. Then you stop there.
Stop there.
Yeah, you already know they are not equal.
Yeah.
Because if they were equal, then everything would be 0.
They are not equal.
That means they are not equal.
Right. Because the one on the left now, what if we minus them? If we subtract them, we get what is on the right. Like we get like x squared. You know what I'm saying?
I don't fully get, but let's use an example. So this P of A, right?
Yes.
Then we said minus P of B, alright?
Yes.
So this is now the polynomial that we're trying to test.
Yes.
Now if P of A and P of B were the same, this would be 0, right?
Yes.
So that means that regardless of how many points you evaluate it at, you always get 0 as the answer, right? So that way, if you do like 102 evaluations and they were all zeros, then you know that they were P of A and P of B are exactly the same. That makes sense, right? Now, in the event that they are not the same, then you are going to get a polynomial that is not a zero polynomial. Meaning that only at d points will it evaluate to 0. And you don't want to be unlucky, that the d points that you pick are exactly the ones that are its roots. So that's why you evaluate at d plus 1 point. So you can, by chance, exhaust all the d roots, but then the next thing is definitely not going to be a root. So when you evaluate it at that point, it's going to be non-zero. But at any point in your evaluation, you could have seen a non-zero. If you say a non-zero, then that means that you can stop there. They are not the same. Because if they were the same, it will always be 0.
But if it's more than a degree, you cannot say it's
If it's more than a degree,
like if
yeah, if they're all zeros, I think if they're all zeros at more than the degree points, yes, then they are the same. Because it's 0. It's a 0 polynomial. Does it make sense? Yeah.
We are assuming that that x plus 5 is the first polynomial. The x minus 6 plus 5 is the second polynomial, right?
So this is the first polynomial,
Okay, that's the first.
and this is the second.
Okay.
So we subtracted that from this, or subtract that from that. It doesn't matter. Like if they're the same, it's always 0. Does it make sense? Any questions?
Yeah, question. So you use the degree of the polynomial does not actually give us the roots of the polynomial.
The degree of the polynomial tells you how many roots the polynomial has.
So like the definition of roots is that if you evaluate it at
A root is
that
0.
value, it will give 0.
Yes.
So if you evaluate a zero polynomial
Yes.
at more than the roots,
That's more than.
it
So
will give 0.
yes. A 0 polynomial, very anywhere is always 0.
Yeah, so that means that the degree of the zero polynomial does not actually tell us.
No,
about
no.
it.
That's excluded.
So okay, that means it works for all polynomials except zero polynomial.
That's what makes the check possible in the first place.
Yeah. And then basically your Schwartz-Zippel lemma stuff, you said it's also with d plus 1.
I'm saying D is also with D plus
It's also
point.
with d. What was
But we'll check.
what was the definition again that you gave?
I was like, if two polynomials are different, 2 degree D polynomials, right?
Okay.
So let's say you had one polynomial and you had another polynomial, both of them were quadratic, right? If they are not the same quadratic polynomial, then they will only evaluate to the same value at 2 points. 2 points. So we're having a back for whether it's 2 or 3 points.
Okay, so if it's more
Wow.
than 2,
It is more than,
if they evaluate to the same value at more than 2 points, it means they are the same.
yes.
I think that's it, man. Because if based on that definition of what was it, to get the diagram or what you call a line of a polynomial, you must evaluate it at d plus 1 point. Right, so if two different polynomials evaluate with the same value at d plus 1 point, it means they have the same curve.
Yes.
Yeah.
So yeah, it has linked it to what you were asking, right? So it's saying that that's why you need D plus 1 points to be able to uniquely describe let's say a quadratic polynomial. You need like 3 points to uniquely describe it, because of 2 points can be shared by multiple quadratic curves. So that plus 1 is like the differentiator, kind of. But yeah,
What
that's.
what if the two polynomials are not of the same degree?
So you use the maximum degree for all your analysis.
Yeah, so it's d points.
Yeah, should be different.
Not d plus 1.
It should be different. Yes. But we'll check you there to see which one is which before we're gonna teach you to rush.
Because if they are not of the same degree, you pick the max.
Yes, it's like padding. You can pad the other polynomial.
Max is
0.
like the maximum.
Yeah,
So
that's what you use your analysis for.
So if you go back to that polynomial,
Well,
Yeah, this polynomial.
is it necessary to is that what you can like since you are saying that the one on the right is basically smaller than the right, so we are assuming that the one on the right is like the big C bar. See, the one on the left, it's possible that when you evaluate it,
When you simplify it, yes,
because they can cancel and cancel.
yes.
So it's safe to just use degree on the right and stuff to evaluate it, for example. You can't be sure anyway.
You can't be sure. But I get what you're saying.
Yeah. Instead of going to 102.
Let me see.
That means you should be degree of the
But if they were not the same, right, then that's risky. Because of it could align with that one at those three values that you pick.
You don't want to expand it yet because
It's too big. So the thing now is that two polynomials might be different, but one polynomial is fully embedded in another polynomial. I don't know how to use it. It's like over the points that you want to evaluate at. And then the state of things is the same, sure. But it's like you can create, let's say, one polynomial from the values of another polynomial plus some. I don't know if you get what I mean. So like if you're only evaluating at that shared domain, then it will look like they are the same until you go outside of that shared domain. Don't know if you get what I mean. Maybe like if you had like something. Oh, sorry. I feel like you can have another polynomial that maybe like goes the same way, maybe up until this point, and then maybe now like goes that way, right? There are going to be a lot of points here, more than D points, right? So you won't really know now until, I don't know if this is like correct reasoning though. But I don't think it's safe to just use the smaller. I don't think it's safe to just use the smaller. Like it's trying, we said max of D, right?
Yeah.
So he is trying to say mean of D.
It's max of D.
You cannot just
Give
say
it
it's max of D.
No, that's not even the max of D.
You are saying mean of
That's
D.
not the max of D. Because until you subtract before you carry it out, because the subtraction.
Yeah, but you can't. You're assuming that you cannot do like the subtraction. That's like you can't simplify this. You can't simplify it. What is not the max of D?
Since the subtraction, you
Mhm.
want to get max of D.
Mhm.
You don't know that, you can't say that as max degree since the guy is evaluated as subtraction. The one you evaluated as max.
It might simplify down to something,
Yeah.
a smaller degree, right? But the point is that we don't want to do the simplification. So we need to pick the maximum degree in both.
Degree and level is the same anyway, so one degree is higher.
If the degrees are, this one, you are seeing it, right? You are seeing it. The degree might actually be the same. You don't know that, right? That's the point. Like when you simplify this, it might simplify down to the same degree as the other one.
I don't even think this one, because one is 101, 100.
Yeah, but yeah,
Still
yeah,
understanding 101, that's just for 101 standard.
maybe yes, exactly.
So it's not like three.
So the problem right now is the fact that I could not come up with like a convincing equation that doesn't make it obvious that one is. So let's check Wikipedia for Schwartz-Zippel lemma. Let me just make sure that it's whether. Let me verify the degree. Can't type. I can type here. Anyway. So it's D. Yeah. Yeah, it's D. Okay. So let's go back. So now, what have we learned so far? If you have two polynomials, P of A and P of B, right? If they are the same and you subtract them from one another, you're going to have what? Right? If they are not the same, This one is for P of A equals P of B, right? Now, if they're not the same and you subtract them, what are you going to get?
P of C.
But there's something we can tell about this P of C, right?
Yeah.
What can we tell?
The degree
What can we tell about the number of points that are zeros on this?
is going to be
Yeah, the number of the degree.
It's still going to be like the max
Only assuming that P of A equals P of B.
degree of.
No, assuming it's not equal.
Okay, assuming
either of them.
He's still going to be like, he's still going to have the like.
Let's now verify that max thing. Is it the max or is it the mean?
No, he's going to have the max.
Is it max?
Yes.
Why is it the max?
It's going to be the max because at the end of the day, what we are not taking our away the x values, for instance. We only like if we are subtracting the numbers, so the x value stands still.
So what it's saying now is that you could have like x3, right? Plus x squared plus 1, right? And then you subtract from just x squared plus 1. The resulting polynomial is going to be x3, which is taking the maximum degree, not the minimum degree.
Or you could also say minus x cubed.
Yes, you could say minus x cubed,
Yeah.
but how do I put it? It's safer
It's safer to assume
is always the same. Because if you now assume it's always the minimum, in this case, you are gone. But in that other case now,
still accounts for both.
you might do like d plus 1, but d plus 1 was too much.
Yeah.
But that's fine, right? Because you better safe than sorry.
So max.
Yeah,
It's something to what's the highest degree? You have the
cancels out.
6%.
And
That's
then
what
to
it's
reduce. But it's still safe to assume the max. Yes, it's not every time it will be the max, but it's safe to assume the max. Okay? So we know now that this P of C is going to be 0 at a max of D points, right? Right?
Yeah, sure.
So if it is 0 at a max of D points, that should tell us something about these two. Like, it's only when you subtract two things that are the same will you get 0. Right? So that means that only D values in P of A and P of B will be the same.
Yeah.
Do you get?
Yeah.
No.
Yeah.
No.
It's coming.
Okay. So we'll do examples soon. We just the theory. Just have to get the theory out first. So I'm coming again now. P of A, P of B. We don't know if they're the same, right? If they're the same and we subtract it, it will be 0, right? Right?
Yeah.
Meaning that regardless of where you evaluate that, it's always going to be 0, 0, 0, 0, 0, 0, 0, 0. Now, if they're not the same, we're going to get another polynomial, right? But we can say something about the nature of that polynomial, right? That polynomial is only going to have a maximum of D zeros in it, right? Then for something, so this is how subtraction works. So the first polynomial, you can think of it as a list. That's like 1, 2, 3, 4, 5. Then second polynomial, you can also think of it as a list. 1, 2, 3, 4, 5. So subtraction is basically like element-wise subtraction, right? So this is going to be 0, 0, 0, 0, 0. This is an example of when both of them were equal. And this is now like the 0 polynomial. But it's not like across the entire domain they are working at. Now, if they were not the same, the only way you will get a 0 at the bottom is if the two of them evaluate to the same value at certain points, right? So let's say this was 6, 2, 5, 4, 6 again. And let me do 7. Right? So now what are we going to get? We're going to get minus 5 here, right? We're going to get 0 here. We're going to get minus 2, 0, and minus 2. So now this is the final P of C. This is technically like P of A. Then this is P of B. This here is P of C. So now P of C is only 0 at 2 points. But then what does that say about the P of A and P of B? It means that they were only the same at 2. Does that make sense? So it's only when they're the same will you, yeah,
They evaluated to minus 2 at 2. So what happened?
the P of C.
Oh, okay.
That's fine, right?
So what you're saying, I can't see this year, so I'm sure that that P of C will not have 0 at more than
D points. And then that also tells you that P of A and P of B cannot have the same values at more than D points. At more than D points. So like now, they have the same values here, and they have the same values here. If they have the same values somewhere else, like here, then you have another 0, which will violate the degree thing that we just talked about. You get?
So why?
This is a key idea. Like this is the underpinning of almost everything.
I'm just trying to understand how the when they have the same value, will it come to play in evaluating, getting how two roots are similar? Because at the end of the day, like they could have the same values at say the third one, like that third one. You say it will validate what you just said. How does that come into play exactly?
Like we already said that if let's say P of A was degree 2, right?
Yes.
Degree 2,
Yes.
and P of B also degree 2.
Yes.
Then when you subtract it, you're either going to get a 0 poly, or you're going to get a polynomial that is like P of C, right? That is also going to be degree 2,
Yeah, possibly.
right?
Yes.
So that means that this polynomial will only have 2 zeros.
Yes.
So if
Based on the power, yes.
yes, so if polynomial only has 2 zeros,
Yes.
then that means that these 2 also can only be the same at 2 points.
When you say two, are you saying they are coefficient or when you
When you
rate
evaluate,
them at their roots?
when you evaluate.
Okay. Yes.
So that's like there are only 2 values of x that you can pass into both of them, that it will give you the same.
Yes.
still doesn't make sense.
So then, are you not saying that this one that I use as example now,
Yeah.
we should evaluate this man
These are the
at
evaluations.
this point where they gave 0, we are going to get 0 for. If we evaluate them at 1 and 3,
So if you look at P of C now, you see the place where there are zeros.
yes.
Must mean that if you evaluate P of A at those points, they will have the same values.
Okay, they will have the same value, not
Yes.
necessarily.
That's why subtraction will give you 0.
Yeah.
Hmm? Yeah, we can prove it. I'm sure we can prove it. I want you guys to go and eat though. But
You're not going to example again.
we'll do an example. By 10. By 11, I mean.
Example, if for instance I put the root of one to the other equation,
You put the root of
one of the one is maybe for instance the root of A, and you evaluate
No, not necessarily. Because we're not necessarily talking about roots for P of A and P of B now. We're talking about roots for like P of C. And that will tell us where P of A and P of B are equal. So basically the roots of P of C are the points where P of A and P of B are equal. But the fundamental idea that I'm trying to drive at is that because of this, you can say that if 2 polynomials are different, they will only have the same values, the same evaluations at D points. That's like, there are only D values of X that when you evaluate P of A and P of B at, that they will be equal.
What is that becoming?
This D is the maximum degree of P of A or P of B. Those points are the roots of P of C. You guys should go and eat.
This d value of x, p of x, p of
We'll do an example, don't worry. So you guys should just go and eat. Come back by 11:30. Then we'll start again.